Very good. I want to welcome everybody. So you're going to see the whole slideshow, and that's just fine. All right. So, good evening, everyone. Those of you in person here in the beautiful Isabel Bader Theater and online, welcome to the 2026 J. Tuzo Wilson Public Lecture. My name is Paul Kushner, and I'm the chair of the physics department here at the University of Toronto. I want to thank the former chair, physics chair Kim Strong, from whom I've drawn these notes that I'm sharing with you today. I'm building on those. So let me begin with the official U of T statement of acknowledgement of traditional land. I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. And in the spirit of this statement, I hope that tonight's Tuzo Wilson lecture deepens our appreciation of the interconnected nature of our Earth and its many living, chemical, and physical systems. The Wilson Lectures honor the life and work of John Tuzo Wilson, who lived from 1908 to 1993. And as the slides flash by, I meant to have them go a little more slowly, but you'll see different scenes from the varied life of Professor Wilson. He was a key discoverer of plate tectonics, a leading figure in Canadian science, and truly an ambassador of science for Canada and the world. In his lifelong study of the Earth, Tuzo Wilson was convinced that beneath all the chaotic wealth of detail in a geologic map lies an elegant, orderly simplicity. His wonderful capacity to assimilate disparate pieces of information and create a coherent physical understanding of the Earth's dynamic crust helped transform our understanding of the global Earth system. I said the word assimilate, and you might hear that word later in tonight's presentation. So Professor Wilson was the first Canadian graduate in geophysics through U of T's Math and Physics program. He graduated in 1930, and then he headed to Cambridge and then Princeton, where he earned his PhD, and then the Geological Survey of Canada, and during World War II, he served in the Royal Canadian Engineers. After that, Professor E.F. Burton, the head of physics at U of T, recruited him back here in 1946 to become the first professor of geophysics in Canada at that time. So through that time, for over 30 years, and in particular from 1961 to 1967, he became a major player in creating the theory of plate tectonics, which was this new global view of how our Earth works, including the ideas of ocean floor spreading and continental drift. His accomplishments are many. He was the supervisor of a large number of PhD students and graduate students of various kinds, many of whom are here tonight, and his legacy lives on that way. But well beyond geophysics, he played many, many important roles. He served as the first principal of Arundel College, which is now the University of Toronto at Mississauga. He served as the president of the Royal Society, as well as the director general of the Ontario Science Centre and Chancellor of York University after retiring from the Ontario Science Centre. So his many accomplishments and accolades can be found, online. But really, this series is really in honor of him. And each year, we have a Wilson lecture in his name. And today, I'd like to introduce the new J. Tuzo Wilson Professor of Geophysics, Professor Dylan Jones, whose image is on the screen now. Professor Jones is a member of the Earth, Atmospheric, and Planetary Physics group in the Department of Physics at the University of Toronto. His research continues very much in the spirit of Professor Wilson's, revealing connections between regional systems and the global Earth system. It is focused on integrating surface, aircraft, and satellite observations of atmospheric composition with global atmospheric models to understand how pollution influences the chemical and dynamical state of the atmosphere. In particular, his work seeks to better quantify emissions of environmentally important trace gases and assess their impact on air quality and climate, and to examine the influence of climate change on atmospheric composition. A bit of Professor Jones's background. He He was a student of Harvard University all through. So he arrived in Harvard a teenager in 1986, and as we were just saying before the talk tonight, he left Harvard a married man with a kid, with a family and children, and came here to Toronto. Along the way, from 1986, he obtained his BA there in 1990, his MSc at Harvard in 1994, and his PhD in 1998. So he was very well educated at that university, and so we were very fortunate to have him join us here in 2004. He held a Tier 2 Canada Research Chair here at U of T from 2004 to 2014, and since then he's held positions as a distinguished visiting scientist at NASA's Jet Propulsion Laboratory and visitor positions at UCLA as well. He's also played important leadership and advisory roles, such as serving as a member of the science teams for the Orbiting Carbon Observatory 2, which is OCO2, and the Geostationary Carbon Cycle Observatory, GeoCarb. He's also been a member of the steering committee for a project called Analysis of Emissions Using Observations, AMIGO. And around 2016, he served as a member of the National Academy of Sciences committee, which was studying the future of atmospheric chemistry research. So really key committee work and very important roles in the science that he's going to describe today. Here at home, he's a wonderful colleague to us in EAPP, our group within the department. He's a fantastic teacher, a great mentor to his students, many graduates over the years, and some of whom are here today. So Professor Jones will hold this professorship for a 5-year term. This is his first year. So as is the tradition in the Wilson Professorship, the chairholder presents the inaugural lecture. So that is why we have a University of Toronto presenter tonight. It is in fact the chairholder. And then it's going to be his responsibility to organize the lectures over the coming years. So that for the next 4 years, there'll be a new speaker each year, and Professor Jones will be in charge of the lecture then. So the topic of his lecture tonight illustrates his work to help us understand connections between different parts of the Earth system. So I'm looking forward to his insight on the many processes involving carbon in the Earth system and how we can use observations and models to track them and thus gain a deeper understanding of our changing climate. So with that, please join me in welcoming tonight's J. Tuzo Wilson lecturer, Professor Dylan Jones.
So first let me start by thanking Paul for that really kind introduction, and I'd like to thank the nominating committee for selecting me as the J. Tuzo Wilson Chair. It's really an honor to be able to serve in that capacity here at the University of Toronto. So for the lecture today, I thought I would tell you a bit about our ongoing work studying the global carbon cycle using satellite observations of CO2. Now, in any talk on atmospheric CO2, it's almost a requirement to show this Keeling curve. So this curve here on the left shows the measurements of CO2 taken at Mauna Loa as a function of time. These measurements were started by Charles Keeling in 1958, which was the International Geophysical Year, and they've continued ever since. The plot here is showing the amount of carbon dioxide in this unit called parts per million, ppm, and I'll be talking about that a lot. What that means is that for every 1 million air molecules, one of those molecules will be a CO2 molecule. So we're talking about really small amounts of these gases in the atmosphere, and we refer to them as trace gases. But they clearly have significant impacts on climate despite being in the atmosphere in trace amounts. What you're seeing here are plots of monthly mean estimates of measurements of CO2 in red, and you can see this nice variation up and down, which is the seasonal cycle. And that's being driven by the greening of the biosphere. So the land biosphere, you have this seasonal greening. In summer, we have this expansion of green on the planet due to photosynthesis, and you can see that driving these changes here, and I'll talk a bit more about that. If we remove that seasonality, we get this black line that shows this nice clear increase in CO2 with time from 1958 to the present. Currently, we have about 425 ppm of CO2 in the atmosphere. To put that in context, during the pre-industrial period, atmospheric CO2 was about 280 parts per million. So we've seen a 50% increase in CO2 in the atmosphere since the pre-industrial period. Now, what's really interesting is that if you go back to the last glacial maximum, when the ice sheets on the planet were at their maximum extent, CO2 concentrations were about 185 parts per million. So from the last glacial maximum to the pre-industrial, there was a 50% increase in atmospheric CO2. And human activity has added another 50% in CO2. So it's really an unprecedented perturbation to the atmosphere with significant climate implications. Now, Charles Keeling chose this site because it's what we call a background site. It's in the middle of the ocean, it's removed from strong sources and sinks, and as a result, you get this fairly nice, smooth variability that we see here. And that masks the fact that these changes in atmospheric CO2 reflects the interplay of a number of complex processes within the Earth system. And you can see that here in this schematic that shows some of these processes that influence the global carbon cycle. So you have photosynthesis, which I talked about, this seasonal greening that pulls down CO2 from the atmosphere, but plants also, you have respiration from plants that releases CO2 to the atmosphere. There's soil respiration that will release CO2 to the atmosphere as well. CO2 can get dissolved into the surface ocean, so there's ocean uptake. Aquatic organisms in the surface ocean can also take up CO2. You have ocean circulation that will take some of that CO2 from the surface ocean down to the deep ocean. Some of these aquatic organisms will die and sink to the bottom, taking carbon down to the ocean sediments as well. So there's a really broad range of complex processes that together drive the changes that we see in atmospheric CO2. Now, what I'd like to do is to draw your attention to some of these numbers. I don't want you to pay attention to too many of them, but I want you to focus specifically on this number. This is the photosynthetic uptake. So this is given in gigatons of carbon per year. So 1 gigaton is a billion ton of carbon. So we have about 120 gigatons of carbon that's taken up from the atmosphere through photosynthesis, and then a similar amount is released through respiration. So the system is almost in balance. And then we have about 90 gigatons that are taken up by the ocean and also released back to the atmosphere. Human activity through fossil fuel combustion, land use change, is adding about 9 gigatons to the atmosphere. Of that 9 gigatons that we add to the atmosphere, about half remains in the atmosphere. So we're seeing maybe about 4 gigatons contributing to this annual increase in CO2 that we just talked about on the Keeling curve. So, as I said, half is remaining in the atmosphere. Where's the other half going? Well, the biosphere, so we have uptake from plants, we also have uptake by the ocean. So the atmosphere and the ocean are taking up almost equal amounts of CO2 and contributing to a rise in atmospheric CO2 that reflects half of what we're adding to the atmosphere. Now, we have 4 gigatons that reflects the change in the atmosphere, and then we have 120 gigatons being taken up by photosynthesis. So small changes in this photosynthetic uptake or the release from of carbon from respiration could potentially dramatically change the amount of carbon that ends up in the atmosphere. So the key point here is that the ocean and the biosphere are really important in controlling this annual increase that we see in CO2 in the atmosphere. And we can look at the atmospheric growth rate. So this is a plot showing the amount by which CO2 increases in the atmosphere every year in terms of parts per million, these units that I talked about. From 1958, when Keeling started making these measurements, to the present. So the bars are showing the increase each year in ppm, as I said. So you have typically about, going back to 1958, about 1 ppm increase per year. But you can see that the amount by which CO2 is increasing in the atmosphere is itself increasing in time. And this increase is really due to the fact that our emissions are also increasing over this time period. The black horizontal lines are showing you the 10-year averages. So you can see the pointer's sort of faint. So you can see how it's changing in time. But if you look at the blue bars, there's tremendous variations from year to year. Some years, the increase is quite large, and in other years, it's quite small. Now, this is actually an interesting feature. If you're curious enough to ask me a question about it during the Q&A, I'll be happy to talk a bit about it. So that's a bit of a setup for questions. But you can see there's just tremendous variability. And this is really due to the land biosphere. So we're seeing changes in that 120 gigatons of carbon that's being taken up through photosynthesis or released for respiration that's driving changes in the accumulation of CO2 in the atmosphere. So the land biosphere and the variability of the land biosphere is really critical. And you can see that really nicely in this animation from our colleagues at NOAA. This is a very complicated animation, so let me set it up for you before I let it run. What you'll see here are measurements of CO2 as a function of latitude, starting from the South Pole through to the North Pole. This is showing you the measurements starting in 1979. Each circle here represents a station that's shown here on the map, so you can see where the stations are located. And as the animation runs and time progresses, you'll see more stations coming online measuring CO2, and those stations will show up here as well. And as the animation runs, due to increasing CO2 emissions from fossil fuel combustion, this line will rise as the CO2 concentration in the atmosphere increases, and the Keeling curve will be shown on the right. So let's run the animation. And I want you to focus on the blue circle, which is the South Pole, the red circle, which is Mauna Loa, and then look in the mid-latitudes between in the northern hemisphere between 30 to 90 degrees north. So as more stations come online, you can see the variations that are occurring here. So you see the seasonal cycle, the drawdown, the increase, the drawdown, the increase as the biosphere breathes. But there's a fair bit of variability. And as we get more and more stations measuring CO2, that variability becomes even more obvious. So it's there, but with more stations, we can pick up that variability more nicely. And you can see here the Keeling curve showing the variations at Mauna Loa in red and at the South Pole in blue. So I'm just going to stop that. Yeah. Significant variation. So this is the influence of the land biosphere on atmospheric CO2. So it's quite critical. And what this means is that for our computer models that are trying to simulate changes in atmospheric CO2, if we're trying to make projections as to how atmospheric CO2 levels will change in the future, we need to be able to simulate this variability well. We need to be able to simulate these changes in carbon fluxes in the biosphere. So the obvious question here is, how well are we able to simulate these fluxes in our computer models? Right. So here's a snapshot showing just 4 different computer models. These are models that are trying to simulate the global carbon cycle with varying degrees of complexity. And this is a snapshot just for summer. So when we have this summer drawdown of CO2 due to photosynthesis across the northern hemisphere, and you can see that nicely, the blue colors represent the loss of CO2 from the atmosphere. So this is the photosynthetic uptake, and the red colors represents the source of CO2 to the atmosphere. So all of the models, as you would hope, are capturing this photosynthetic drawdown, which is great. But if you look at the details, so you have SIB3 and compare that to the CTEM model, large differences in the strength of that drawdown. Right? The colors here, you have much stronger blue colors in CTEM compared to SIB3. Right? So very large differences in what these models are telling us as to how much CO2 is being taken out of the atmosphere. This is just a summer snapshot. We can now look at the seasonal cycle, so how these fluxes are varying over time, over the whole year in the various models that we considered in this study. And let's focus just on the northern mid-latitudes where we have most of the boreal forests across North America and Eurasia. So that's what's plotted here on the right. This is showing gross primary production, which is photosynthetic uptake, and the respiration on the bottom, which is the release of carbon from plants and soils. The different lines represents the different models, so the 4 models here plus a few other models. What I want you to focus on is just the large difference between the different models. The green line here is the SIB3 model, So this is showing the seasonal uptake from photosynthesis as simulated in SIB3. And you can compare that to CASA, which is blue, which is showing significantly stronger uptake. The CASA model has about 50% stronger uptake than the SIB3 model. So what are the implications of this if you're using these models to make projections as to how CO2 levels are going to evolve in the future, given the large differences that you see between these models? So that's the main take-home message that I'd like you to get from this slide, is that there's a large spread between the models, and if we can measure CO2 in the atmosphere accurately and precisely, then can we use the observed changes in CO2 to inform these models, to get a better understanding of the underlying processes in the models and reduce this uncertainty, this spread, and hopefully in doing so, make more reliable projections as to how CO2 levels will evolve in the future. So that's the hope. That's the plan. The challenge here is that the system is incredibly dynamic. Now, this is an animation showing a computer simulation of CO2 from Environment and Climate Change Canada. It's a one-year simulation for 2010. And the white colors represents high concentrations of CO2. The darker colors are low concentrations, so you can see higher concentrations in the northern hemisphere, where we have more pollution, and the land biosphere, and then darker colors in the southern hemisphere, where it's mostly ocean. As we proceed into summer, you'll see the summer drawdown occurring, and you'll see the drop in CO2 as the colors become dark. But the main point is you can see chemical weather. You're seeing the weather patterns acting on these CO2 fluxes, driving these dynamic changes in the system. So if we want to measure CO2 in the atmosphere and use those measurements to say something about what the underlying fluxes are doing, we need to be able to capture all of this variability fairly well. That means we need to be able to sample the system densely in space and in time. Let me just stop the animation. If you emit a pulse of CO2 over Toronto, that CO2 signal will get transported by these winds and mixed into the atmosphere across the northern hemisphere. And that happens on a time scale of 30 to 60 days, so 1 to 2 months. So if you're making a measurement once a month, and you're trying to use that measurement to say something about how much CO2 was emitted from Toronto, that temporal frequency, that's not frequent enough to allow you to use the measurement to say something about what was happening in Toronto. You need to be able to sample the changes more frequently, given that within that 1 to 2 month time scale, the signal gets well mixed throughout the atmosphere. And then the time scale for mixing from the northern hemisphere to the southern hemisphere is about 1.5 years. And since most of the anthropogenic, the fossil fuels emissions are in the northern hemisphere, typically you see a lag for when that signal will show up in the southern hemisphere. And so that's why if you were looking at that animation from NOAA at the blue dot versus the red dot, you can see the difference in the timing between the southern hemisphere at the South Pole and Mauna Loa in the northern hemisphere. But the main point is you really need to sample the system very densely in space and time. And if you look at the surface observing network, this is the network from the Global Atmospheric Watch. So this is a greenhouse gas measurement network that consists of ground-based sites, aircraft measurements, ship measurements. You see that there is a fairly uneven distribution of measurement sites. I'll talk mostly about the ground-based measurements, so let's focus on those, which are the red circles. So you can see we have good clustering in Europe, fairly good coverage over North America. But as you look across Africa, South America, across Australia, much of the southern and tropical ocean, there's just a significant lack of measurements. So if we want to use these measurements to say something about the fluxes, the underlying fluxes and how they're changing in time, it's really difficult to do that if you're interested in how the fluxes in the Amazon might be changing or how fluxes in the Congo Basin might be responding to climate change. And it's this discrepancy that really drove us to making measurements from space. The idea is that if we can measure CO2 in the atmosphere from space, we can get a much more uniform coverage across the globe and use that information to inform our understanding of these underlying fluxes. So the first satellites that were built to specifically to measure CO2 were the GOSAT, the Greenhouse Gas Observing Satellite. This is a Japanese satellite that was launched by JAXA, the Japanese Space Agency, in January of 2009. And the instrument is still in orbit, working, it's still operational. The orbit repeats every 3 days, which means that every 3 days the measurement returns to the same spot on the surface of the Earth. So it takes about 3 days to get global coverage. The measurement, the satellite sees a circular area that we call a footprint with a diameter of about 10 kilometers. So it's really measuring about 100 square kilometer region of the surface of the Earth. So it's a fairly large region, which of course makes it really difficult if you want to use GOSAT measurements to look at CO2 from a city, for example. 100 square kilometer captures pretty much of the GTA. So you couldn't really use these measurements to say something about Toronto fluxes. But the mission is still operational, it's still in orbit. At the same time, NASA built the Orbiting Carbon Observatory, OCO, and that was launched 1 month later on the 24th of February 2009. And that was a beautiful launch. It was launched from the Vandenberg Air Force Base in California. On that night, it was dark, the moon was not up, it was cloud-free, it was just beautiful. And you were able to see the launch for quite some time. And this picture from one of our colleagues shows that beautifully, capturing the launch from Vandenberg. Unfortunately, the next day, this was the headline in the New York Times. NASA satellite fails to reach orbit. And all of us on the science team were pretty crushed upon seeing this. And the problem was that the instrument was launched using the Taurus XL rocket. And there's a device called a fairing that encloses the instrument. And that failed to open to release the instrument in orbit. And so it was too heavy to stay in orbit and ended up returning to Earth, landing in the Pacific off the coast of Antarctica. Fortunately, David Crisp, the PI for OCO, and the NASA team were successful in getting funding from the Obama administration at the time to rebuild the instrument. And the hope was to get a second instrument in orbit very quickly. But 2 years later, in March of 2011, NASA launched an instrument called GLORY to measure aerosols, particulate in the atmosphere, using the Taurus XL rocket, and exactly the same thing happened. So that ended up also in the Southern Ocean. So together, the cost of OCO and the cost of GLORY was about $700 million, and that hardware is sitting in the Southern Ocean off the coast of Antarctica. And that was the third failure of the XL launch within a decade. There was also a failure, the same thing with the fairing, in 2001. So the decision was made not to use the Taurus XL rocket to launch this rebuild of OCO. And as a result, the instrument sat on the ground for quite some time. And finally, on July 2nd, 2014, OCO2 was launched from Vandenberg. And this time, NASA used a Delta II rocket, and that was a flawless launch. It's very cloudy. We did not get to see the launch except on the screen, but it was successful, and that was excellent from our perspective. So the OCO2 instrument has a 16-day repeat cycle. So it makes about 233 orbits per cycle and repeats every 16 days. So it takes 16 days to repeat the orbit and see the same spot on the surface of the Earth. The instrument has a fairly high-resolution footprint of about 3 square kilometers with a 10-kilometer wide swath. So the animation here, which we'll repeat, shows that 10-kilometer wide swath that's as the instrument flies along, and within that swath we have these high-resolution measurements that are about 3 square kilometers. 4 years later, in October of 2018, the Japanese launched GOSAT-2, the second version of that instrument. And this time it had a longer repeat cycle of 6 days as opposed to 3 days. And then 1 year later, NASA launched OCO3. David Crisp was able to obtain enough funding to build OCO2 and have enough parts for a spare instrument, OCO3, which was launched in May of 2019, and that was placed on the International Space Station. And because of its orbit on the space station, OCO3 can only make measurements equatorward of 52 degrees. So we really can't see the high latitudes in the northern hemisphere nor in the southern hemisphere. Now what's really nice about OCO3, and I'll talk about that later, is it has this special measurement mode called the snapshot area mapping mode. And as you'll see later on, there's tremendous value with that approach. So with these instruments, we ideally have significantly greater observational coverage. So we can now try to compare the observational coverage that we get from these satellite instruments to what we're getting from the ground-based measurements. This plot is showing, the distribution of ground-based sites. So it's similar to the plot that I showed you before, but now it's color-coded. So the ground-based measurements are point measurements, but the filled circles are telling you the number of observations per day that you get at each of the different sites. And depending on the type of measurement that's made, it varies anywhere from less than 1 observation per day to as many as 10 observations per day. But again, you can see the clustering of the sites in the northern hemisphere over North America and Europe. There's also another ground-based network called the Total Carbon Column Observing Network. This is a network of ground-based Fourier transform infrared spectrometers that are looking up at the sun to make greenhouse gas measurements. This network was designed in support of the OCO mission as a way of making measurements that can validate the satellite measurements. So ground-based measurements that can validate what we're seeing from space. But over time, the network has grown, and it's now providing valuable complementary information from what we're getting from the satellites. So there's tremendous science value now in these measurements beyond just validation of the satellite measurements. And the chair of this network is our colleague, Professor Deborah Wunsch, here in physics. So it's a really unique set of measurements that have significant science value. And then we have the satellite measurements. So you can see here that we're filling in the information across the tropics with GOSAT and OCO2. The OCO2 footprint is about 3 square kilometers compared to the 100 square kilometers for GOSAT, so we get much greater observations. These satellites cannot see through clouds. I'll talk a little bit about how we make these measurements shortly. So if you have a fairly small footprint, your chance of seeing between clouds is much greater. And so we have much greater coverage. We make many more observations with OCO2 than we're able to make with GOSAT. And you can see that showing up very nicely. Significantly greater coverage in the tropics. Now we can ask, what's the sensitivity of these measurements to the surface fluxes? Because ultimately, what we want to do is to use the surface measurements and the satellite measurements to say something about the fluxes. So given that we know where the measurements are being made in space and time from both the ground-based network and the satellite networks, can we sample our models and calculate how sensitive the models are at the locations where the measurements are being made to the surface fluxes to tell us the potential utility of these measurements for informing the fluxes? So that's something that was done by former student Brendan Byrne, who was working with me and Professor Kim Strong here at U of T. So Brendan sampled our model where these measurements were being taken in space and time and calculated these sensitivity maps. So this is showing you how much atmospheric CO2 changes in parts per million per unit change in surface fluxes. So if we look at the ground-based network in the top, I should have mentioned, that the different columns represents the different seasons. The first column is fall, September, October, November. Winter, December, January, February. Spring, March, April, May. And then summer, June, July, and August. The top row shows the ground-based network sensitivity. The red colors means we have significant sensitivity to the surface fluxes, and the gray colors represents where the sensitivity exceeds the color scale that we've selected here. So across North America and Europe, there's significant sensitivity all year long, but across the tropics, you can see that the sensitivity is quite weak with the ground-based network. I'm going to use this cursor because the laser pointer is not working too well, and that will be better perhaps for the folks online. However, with the satellites, we start to see that sensitivity in the tropics really showing up, especially with OCO2, where we have much greater observational coverage. And particularly in the summer months here, the northern summer, just a significant sensitivity because of the wealth of observations that the satellite is providing. So you might think, well, given what we're seeing here, maybe the story is not to use only the satellite observations, but to think about combining the satellite data with the ground-based measurements that gives us the sensitivity across the tropics as well as that sensitivity to the fluxes of the higher latitudes. And indeed, that's what we do. Okay, so how do we measure CO2 from space? The satellites don't actually measure CO2. What satellites see is radiation coming up from the atmosphere. And CO2 is a greenhouse gas, so it absorbs thermal infrared radiation. That's what greenhouse gases do. They absorb thermal infrared radiation coming from the Earth, and reduces the efficiency at which the Earth can cool by radiating to space, and that leads to warming. So that's the greenhouse effect. CO2 has a very strong absorption, around 15 microns, which is the key part of the infrared spectrum. And some satellites use that part of the spectrum to estimate CO2. GOSAT and OCO2 do not use that part of the spectrum, because if you look in the thermal infrared part of the spectrum, you have the ground radiating as a warm body, and the air just above it is also radiating at a similar temperature, and you can't discriminate between the radiation coming from the ground and the radiation coming from the CO2 molecules just above it. So there's no sensitivity. So instead, what we do is we look in the shortwave infrared part of the spectrum, so around 1 to 2 microns, where we have significant reflected sunlight, and you have sunlight coming in, reflecting off the surface, and CO2 is absorbing that sunlight. So the satellite is seeing the absorption signature of the CO2 molecules in that column of air. And we can use that absorption signature to estimate how much CO2 must have been in that column, given what the satellite has measured. So that's how we do it. And because we're looking at reflected sunlight, we have more sensitivity near the ground, and we want to measure the CO2 as close to the surface as possible, because that's where the fluxes are located, and we want to capture those changing fluxes at the ground so that we can use the satellite information to better understand what's going on with the fluxes. Now, you're getting this vertical integrated estimate of the total amount of CO2 in the atmosphere, and we report this integrated amount in these funny units that I'm going to define for you, because I will use the term XCO2 throughout the talk, so you should know what it is, even though you'll forget about it within half an hour after the talk. But we define it as this column average dry air mole fraction. Okay? So there's a mouthful there. And we try to account for the amount of water vapor in the column, because as the weather patterns change, the amount of water vapor in that column changes. And water vapor can be as much as 3% of the air. So you don't want to see variations in the CO2 that's actually variations in water vapor. So we have to remove the water vapor when we report the CO2 as measured by the satellites. And also this column, the depth of the column changes as the surface topography changes. On top of a mountain, you have less air than at sea level. So you have variations in the total mass of that column as the surface topography changes. And that could also look like a variation in CO2. So we need to account for that as well. And that's what this XCO2 quantity represents. So I'll talk about XCO2. You'll see XCO2 in the slides. The details are not that relevant, but it's important just to mention what they are. Okay, so we have these measurements from the satellites, and we can now feed these into our models to try to estimate the fluxes. So the inverse modeling framework is one in which we start with some guess as to what we think these fluxes are, our best guess of the fluxes, and we pass those through our atmospheric model to simulate the CO2 distribution, and then compare that simulated distribution to the satellite observations to look for discrepancies between the two. And then we can adjust the fluxes to reduce that discrepancy between the two, to bring them into agreement, given the uncertainties of the observations and the uncertainties of our model. Right? So in doing so, hopefully we end up with a better estimate of the fluxes that are consistent with what the satellite is seeing in terms of CO2 in the atmosphere. And ultimately, the goal here is to link robust estimates of the regional sources and sinks to the process-based models, to improve our understanding of these processes in the biosphere. So going back to that earlier slide where I showed the 4 arbitrary models, ecosystem models, really we want to get a better understanding of the processes driving the fluxes so that we can reduce that spread between the models, and hopefully in doing so, ultimately make more reliable projections as to how atmospheric CO2 levels will evolve in the future. Okay, so I mentioned that we expect to see the greatest benefit of satellite data in the tropics. And so for this part of the talk, I'm going to focus on the tropics. I'm going to show you some results from a study that we did using GOSAT data, but just focus on one part of that study looking at fluxes from South America. So GOSAT was launched in 2009, and in this study, we were looking at fluxes from 2010 through 2013, so just after the GOSAT record. And on the top left, we have the GOSAT observational coverage. This is, I think, October. I don't remember which particular year. And we've color-coded the land data versus the ocean data from GOSAT, just to emphasize the differences. And I have a circle over the Amazon region where you can see that there's a lack of observations. And this is because there's persistent cloud cover in this region. And the satellites cannot see through clouds, and so we have very few observations there. So we were interested in understanding the impact of the observational coverage on the fluxes. Right? I made a point that we need to sample this dynamic system densely in space and time if we want to estimate the fluxes. And so here we have some interesting differences in the observational coverage. So we fed just the land data into our inverse model to estimate what the fluxes are. And for South America, for 2012, you get a picture that looks like this. Oops, that gives away the punchline. So the red colors represent sources of carbon to the atmosphere. So we're seeing the loss of carbon from the biosphere. And the blue colors represent sinks. So we're seeing uptake. So with just the land data, we're seeing this large source of carbon over northern tropical South America, with some uptake in central South America and more temperate South America. When we add the ocean data into the inversion, so we combine both the ocean and the land data, thereby expanding the observational coverage, we get the picture on the right. It's very different. Northern tropical South America turns into a sink of CO2. Right? And we see a strong source now in eastern Brazil. Very different picture. Right? The obvious question is which is right. So we can turn to drought data. 2012 was an interesting year. There was a severe drought in eastern Brazil that year. And what's plotted here is the drought severity index, showing where you had significant moisture shortage and where you had excess moisture availability. And what we know is that where we have reduced moisture availability, you would expect the land biosphere to lose carbon. And so this loss of carbon that we're seeing here is more consistent with the drought conditions in eastern Brazil. And where we have an excess of precipitation, you would expect to have a much more active land biosphere taking up carbon. And so the sink of carbon that we're seeing here is more consistent with the moisture availability that we see here. So having this enhanced observational coverage is really critical in giving us a better understanding of the carbon balance in this region and showing that it's consistent with what we understand the processes should be in that region given the availability of moisture. Now, the way this worked is that because we were bringing in the ocean data, we were relying on our atmospheric model to take any of the signals that are coming from South America and exporting that signal over the ocean. So the predominant winds in this region are from the continent out over the Pacific. And by having measurements over the ocean, we can sample that outflow from the continent and use that information to say something about what's happening in the continent. In the absence of the ocean data, we have little information on what's happening in the continent, and that's contributing to that discrepancy that we see here. So this is part of the inverse problem. For those of you who are statisticians, the inverse problem is an ill-posed problem. What that means is that there's no unique solution. And the solution is very sensitive to the assumptions, the errors in the observations, and in this case, the errors in our model. So these are interesting results, but it's just from one model, and it's possible that if our model is not capturing this export from South America reliably, these flux estimates could be biased. So it's important to keep in mind that when you see the inversion results from any one particular model, you always have to be a bit skeptical and ask, how sensitive are those results to errors within the model? And it's because of that, for OCO2, we created a model into comparison project that brought together a large number of inverse modelers from around the world so that we would have an ensemble of models to combine to look at the mean of this range of models and hopefully get a more robust signal that is less sensitive to the errors in any one model. So I've listed here the various groups contributing to the OCO2 MIP, our Model into Comparison project. We are one of many groups listed here. And just to highlight why it's important to use an ensemble, I have plotted here in the top row an example of the 2019 fluxes from this study showing our model results and the results from a different ensemble member. And I've obscured the institution that's contributing these fluxes, since that's not relevant. But keep in mind, these two models are ingesting exactly the same data. So we're ingesting the OCO2 data plus the surface data, exactly the same observations coming in. But if you look at the fluxes that we estimate, they're very different. Right? So our model has much stronger sources here in Northern and South America compared to this model, where it's fairly neutral. Stronger uptake across Europe, very different. Right? And that reflects the differences in the actual atmospheric models themselves. So even though we're using the same data, there are large differences. And this is one of the challenges with this inverse problem when we're trying to estimate fluxes from the atmospheric observations. It's important, it's an important problem, but it is challenging. However, if you have a large enough ensemble, you can look at the mean across all of these different models, and that gives you a much more robust signal. And this is an example of the ensemble mean. When you simulate both, as Paul said, you can hear simulate, when you incorporate the OCO2 data together with the surface data, and this is comparing that analysis with when we ingest only the surface data. So you can see some slight differences between the two. So for the rest of the talk, when I talk about fluxes, it's going to be in the context of this ensemble mean. That's because we have more robust signals when we look at the ensemble mean. All right, the tropics is where most of the action is occurring. That's where we're seeing we expect to see the greatest benefit of the satellite observations. So let's focus on the tropics. This is showing fluxes for the tropical region is defined by the yellow bar on the top left for the 2015 through 2020 period. So this is the 6 years after the launch of OCO2. And in this analysis, we've ingested only OCO2 data. The green lines, the green bars, show the fluxes from the land. So you can see the seasonal cycle. So emissions of CO2 to the atmosphere, drawdown of CO2 from the atmosphere, emissions, drawdown, and it's varying in time. This period here from January 2015 through 2016 is interesting because you see a much larger source of CO2 to the atmosphere than in any other point in the 6-year period. So that's somewhat interesting. So the question is, what's unique about this time period, 2015 to 2016? Any ideas? I know it's a large auditorium. It's not ideal for back and forth, but can someone shout out what they think was happening in 2015 or 2016? El Nino, exactly. We had an extremely strong El Nino at that time. And there was some very nice work that was done by our colleague Zhenji Liu at JPL looking at this time period, because we were fortunate to have OCO2 in orbit when this El Nino occurred. And what Zhenji showed was that because of El Nino, there was a severe moisture deficit in northern tropical South America that led to a significant loss of carbon to the atmosphere. So a lot of this signal for this year is being driven by what's happening in South America and as a result of the El Nino. But for this particular talk, the main point here is that when we use the OCO2 data, we're seeing a source of carbon averaged over the 6-year period of about 1.35 petagrams of carbon. So that's 1.35 gigatons of carbon to the atmosphere. In comparison, if we use only the surface data, we get about half as much carbon being emitted to the atmosphere. So a significant difference as a result of just using the satellite data as opposed to just the surface data. Now, what's really interesting is that most of this is coming from northern tropical Africa. So the northern tropical African region is defined here at the top right, and the same plot, and you can see if you look at the magnitudes here, a large fraction of what you're seeing across the tropics is from northern tropical Africa. So the numbers are shown here. For northern tropical Africa, we have about 0.9 petagrams of carbon. So that's about 2/3 of the flux of carbon to the atmosphere across the tropics as a whole when we use OCO2 data. When we use just the surface data, the northern tropical African region accounts for a little less than half of the total emissions across the tropics. So significantly more carbon is being lost to the atmosphere according to the OCO2 data, and much of that is happening in northern tropical Africa. And it's possible that this discrepancy is due to the fact that, as I mentioned, the surface observations aren't able to give you enough coverage across the tropics to pick up the changing CO2 signals due to the changes in the fluxes. With the satellite observations, we have much greater coverage, and so we can hopefully pick up that signal better. Okay? That's the idea. It gets really interesting. So we have this nice paper that was written by our colleague, Ben Gobert, at the National Center for Atmospheric Research. And Ben used aircraft observations to estimate fluxes from northern tropical Africa. Particularly, he used observations from a NASA mission called the ATOM mission, so Atmospheric Tomography Mission. And there were 4 campaigns that NASA flew over 4 different seasons between 2016 and 2018. So these are the 4 different campaigns to sample trace gas distribution around the globe. These are really interesting missions in which they flew from Alaska south down the Pacific to off the coast of Antarctica, across to the Atlantic, and then north back to the Arctic. So to get global coverage in these 4 different seasons. And the Atlantic flights, the flights across the tropics and the Atlantic, moving back to the Arctic, were well positioned to capture outflow from tropical Africa. So Ben used the aircraft data to try to estimate how much CO2 is being emitted from the northern tropical African biosphere, given what the aircraft were seeing. And his results are shown on the right. It's a very busy plot. There wasn't a nicer plot from his paper, so you'll have to bear with me with this one. I'll try to walk you through it. But if you focus on the teal line here, this teal line is showing the average flux of carbon to the atmosphere inferred from the aircraft data. And it's about 0.14 petagrams of carbon. And the shaded region is the uncertainty around that. So it's much closer to neutral. It's not a really large source. The other lines reflect the different atmospheric inversions using different combinations of surface data and satellite observations. And those inversions are suggesting a much larger source of carbon to the atmosphere, between 0.1 to 1.5 petagrams of carbon. A very different picture. It could be that, if this is real, it suggests that we don't understand what's happening with the northern tropical biosphere, because we don't know what this source should be. And that has implications for our ability to simulate how the northern tropical biosphere will respond to a changing climate. Now, it could also be that the surface observations are sparse. The aircraft measurements are just 4 snapshots in time. So perhaps those measurements are not enough to give us a reasonable estimate of what the emissions are for northern tropical Africa. It could also be that the satellite measurements are biased, because we can't see through clouds. So the measurements tend to favor the dry season when it's cloud-free. And during the dry season, you expect to have more emission of carbon to the atmosphere than during the wet season when the biosphere will take up more carbon. But we don't know. So it's an interesting puzzle that we're trying to resolve. So the community is still arguing about what's going on in northern tropical Africa. And unfortunately, we just don't have a lot of other observations, complementary observations, to try to answer this at the moment. The community also took advantage of this ensemble of flux inversion results to make a contribution to the global stocktake. Now, the global stocktake is part of the Paris Agreement, in which every 5 years, the parties to the agreement meet to assess their nationally determined contributions. So these are the targets that the various nations set to achieve the Paris Agreement targets. Normally, the nations will carry out what's called a bottom-up analysis, in which they'll look at energy production, industrial energy generation, industrial production and industrial processes, agriculture, forestry, and all the land use changes, as well as waste management and disposal. And based on the the emissions of carbon from these different sectors, the various nations will put together a national greenhouse gas inventory, which then feeds into the national determined contributions, which are the various targets that they set. Just last year, Canada reported their 2035 national determined contributions that suggest that we will aim for a 45 to 50% reduction in our greenhouse gas emissions relative to what we emitted in 2002. So it's a bit of a ratcheting process. Every 5 years, as part of this global stocktake, the hope is that we'll set more stringent nationally determined contributions to achieve the Paris Agreement targets. We are, and as a community, using atmospheric observations to infer the fluxes, which tend to be on a fairly regional scale. So we're looking at a more integrated picture compared to the very sector-specific estimates that we get in this bottom-up process. And so the Committee on Earth Observation Satellite, CEOS, proposed this pilot project to use the inversions to make a contribution to the global stocktake with the hope that combining this atmospheric CO2-derived flux estimates, these top-down estimates, with the bottom-up sector-specific estimates, we can get a more complete accounting of greenhouse gas emissions and removals. This work was led by JPL, and it was done by Brendan Byrne. So after graduating from U of T, Brendan went to do a postdoc at JPL, and of the many projects he worked on, this was this global stocktake project was one of the, I think, the most challenging projects. It's brought together all of the inverse modelers, the measurement folks. So you can see some of our experimental colleagues, Professor Kim Strong, Professor Deborah Wunsch as co-authors on this study. It involved people doing some of the bottom-up work as well. So it's just a very challenging task to bring together the community and estimate changes in carbon stocks for the various countries around the globe. So here's an example of some of the results from this study. And we're just going to focus on the US and the EU plus the UK. The top two plots are just showing the fossil fuel estimates. So in red are the estimates from this analysis, and then we have the national inventories as a black circle. So this is energy generation plus the industrial processes and product use. And you can see that the fossil fuel estimates are all fairly consistent. What's most interesting is the bottom. And the bottom is showing changes in carbon stocks in the land. There's a lot of information here. The different colors represents different inversions. So just focus on the mean differences between the inversions and the reported national inventories, which are the black circles, for both the US and the UK. And just look at the difference. So these are negative values, so that suggests carbon sinks. And what you're seeing is that the inversions are suggesting much stronger sinks of carbon than we're seeing reported in the national inventories. For the US, the inversions are suggesting that the carbon sink is larger by 0.6 to 0.9 petagrams of carbon. For Europe and for the EU and the UK, we're looking at a difference of 1 to 1.8 petagrams of carbon, so large differences. And we don't know what's the source of this difference. Are there sinks that the national inventories are missing? Could this be an issue with the satellite observations? We don't know. But it's a beautiful example of the potential for these inversions to provide a complementary picture to the bottom of information as part of a global stocktake. So this was a pilot study for the 2023 global stocktake. There'll be another one in 2028. And the hope is that as we get more observations, more precise observations, we'll be able to make a much more valuable contribution to the global stocktake. The reason we're showing the US and Europe here is because these are some of the larger regions. What we found was that for the smaller countries, the inversion results weren't statistically robust. And again, the hope is that with more observations, more precise observations, we can hopefully be able to get a better constraint on the fluxes from these smaller countries and thereby make a more meaningful contribution to future global stocktakes. Everything that I've talked about so far has been focused on regional fluxes, and that's because estimating regional fluxes was the science objectives of the GOSAT mission, the original OCO mission, as well as the OCO2 missions. But what we found was that even though OCO2 was not designed to estimate fluxes on local scales, we've been able to do that. And this was some really beautiful work that was done by our colleague Ray Nasser at Environment and Climate Change Canada. Ray Nasser was a postdoc here at U of T and then moved on to ECCC and is affiliated with us again as an adjunct professor in physics. And Ray showed really beautifully how even though OCO2 was not designed to go after power plants, we can actually get information on local scales from these power plants. The plot on the left here is showing an example of an OCO2 tract, so it's just this 10-kilometer wide tract over a power plant in India. This is the Sasan Ultra Mega Power Plant. The arrows show the direction of the winds, and if you look on the plot here, this is showing the CO2 measured from the satellite as a function of the distance from the source. So upwind, you have what we can consider background conditions, and as you approach the source, you can see the enhancement from the power plant showing up in the satellite observations. And this was just beautiful work. On the right, this is another follow-up study from Ray looking at power plants in the United States. So there are two different power plants here, and then this is the same power plant, but the wind direction's changing. So the two arrows, the different colors represent different estimates of the wind, but they give you the wind direction. And again, you can see the enhancement. So it's really, it's just, it was just a beautiful analysis. But the real game changer came with OCO3. And this is this snapshot area mapping mode that I talked about. So within a 2-minute time frame over a particular target, OCO3 is able to make this dense sampling over an 80-kilometer by 80-kilometer domain so that you can see strong enhancements of a power plant. And this, I think, is over the Bełchatów power plant in Poland, and you can see the pollution plume emanating from the power plant. And Ray has shown that the OCO3 data work really beautifully in this case. So building on the work that he did, we looked at estimating the emissions from Bełchatów. And on the top left, we have an example of the OCO3 SAMs for the 8th of April of 2020. So you can see the power plant here in red, and then you can see the signal, the enhancement from the pollution plume downwind from the power plant. Even though you can see the signal, it is still really hard to isolate the pollution plume from some of these measurements, and so typically the community uses measurements of NO2. NO2 is produced when you have high temperature combustion. The high temperatures can break the molecular nitrogen bonds and produce these nitrogen oxides, and you can see very clearly the pollution plume from the power plant showing up here in NO2 measurements from the tropospheric ozone monitoring instrument. So it's another satellite measurement. And we can use that plume signature in NO2 as a mask to isolate the OCO3 measurements that fall within the plume and feed that information into our inverse model. So for this power plant, that's what we did, trying to model the pollution plume. Most of the studies looking at emissions from power plant make simplifying assumptions about the structure of the plume, assuming that it's Gaussian, and that typically works well under ideal conditions, but when the winds are highly variable and the plume is changing direction, it can be a challenge. And so in this study, we were trying to estimate to model the plume directly. And it works fairly well. The plot here on the right shows the emissions from the power plant in kilotons of CO2 per day. Lots of different lines, but just focus on the red line. The red line are the emissions that we estimate from the power plant based on the power generation. And this is shown for 9 different sets of measurements on different days from the 8th of April through the 13th of October 2021. So we have the estimated emissions based on power generation data from the power plant, and all of our different inversions are fairly consistent with that. So this is showing that with the satellite observations, we're able to constrain the power plant emission fairly well. So this is all really impressive given where we were 10 years ago. With the CO2 measurements from space. And as I said, this is just building on some work that Ray has done, and Ray has applied this for power plants across Canada and shows that it works really well for a range of power plants of different sizes. So this has all been wonderful, but as you know, science funding in the US is a bit problematic, uncertain. And as a result, NASA funding for OCO2 and OCO3 will end this September, which is unfortunate for us, given the successes of these instruments. Fortunately, NASA is open to partnering with other organizations and institutions to continue support of these missions. So they were accepting proposals, partnership proposals for OCO3. Those were received in December, and I have not heard of the results of the selection process. They're currently receiving proposals for partnership for OCO2, and the deadline for the proposals is in 2 days from now. And hopefully within a few months we'll hear about the outcome of the selection process. And that will give us a few more years of measurements. For OCO3, the mission will terminate in 2030 anyway, because the space station will be deorbited in 2030. But at least we will get a few more years of observations from OCO3. Despite all of that unfortunate news, it's actually a really exciting time because we're seeing new observations. I'm almost there. We're seeing new observations, new instruments that are being launched. So just last year, we had the third version of the GOSAT instrument, GOSAT GW, that was launched by JAXA, and that will measure CO2, methane, and NO2 with 2 different modes. So there's a wide mode that has a 900-kilometer swath. So if you're flying over Japan, this is what the wide mode will give you. But then there's a focus mode with higher spatial resolution. So if you're flying over Tokyo, for example, you can get more dense measurements to look at the urban scale emissions. And then a month later, in July of 2025, microcarb was launched. This is a joint French-UK mission that will also have a standard mode and a city mode to measure emissions at higher spatial resolution. And then looking forward over the next couple of years, we'll have the Copernicus anthropogenic CO2 monitoring mission, CO2M. This will see 3 satellites launched between 2027 and 2025 to measure CO2, methane, NO2. So the NO2 can be used to go after emission plumes, aerosols at a fairly high spatial resolution of 2 by 2 kilometers. And what's really interesting here is that each satellite will have 50 times the coverage that we have from OCO2. And the focus of this mission is really to monitor CO2 emissions to support the global stocktake. Right? So as I mentioned, we're at the limit in terms of what we can do in going after emissions from smaller countries with the current set of observations. The increased observational coverage that we'll get from CO2M will allow us, hopefully, to get much more robust estimates for the global stocktake at a larger range, over a larger range of countries. And in Canada, we have a really interesting mission called the Arctic Observing Mission that has been proposed. This would be an ECCC-led mission. And so Ray Nasser is the PI for this mission. And this will, if it goes forward, will have 2 satellites flying in a highly elliptical orbit. And what that means is that if you have the satellites flying in highly elliptical orbits, as the orbit approaches perigee, its closest extent to the planet, the satellite will be flying very rapidly as it goes around the planet. But at apogee, at its farthest extent from the planet, the satellite will be flying very slowly. And if the satellite is flying very slowly relative to the rate at which the Earth is rotating under it, it's essentially like a geostationary satellite. It will be able to steer down over the Arctic for extended periods of time to make continuous measurements across the Arctic. So this will allow us, for example, to look at how photosynthetic uptake is changing over the course of the day. All of the other satellites give us 1 measurement per day at a given location. With AOM, we will be able to see how the fluxes are changing over the course of the day. Depending on the ultimate configuration of the mission, we could have as many as 10 million observations per day, cloud-free observations per day across the Arctic. In comparison with OCO2, we have 100,000 observations. So the coverage here really would be transformative if it goes forward. It's still in its early stages, so it's not clear if we will actually get it into orbit, but if it does, it really will be transformative in terms of our ability to monitor the changing carbon balance in the Arctic. And what would be very nice is to have AOM in orbit with CO2M, because these measurements are confined to the high latitudes, to the Arctic, poleward of about 40 degrees. So if you combine CO2M, which gives us this global coverage and high spatial and temporal resolution, with AOM, and we've done some concept studies here at U of T on that, you now have much greater information globally, both at the high latitudes and as well as across the rest of the globe. So it would be a fantastic opportunity for us, and it would be a great Canadian contribution to carbon cycle science if we can make this happen. So I'm just going to close now by saying a few words in terms of where we're going. As a community, we have a roadmap for implementing carbon dioxide and methane monitoring from space. So this roadmap was proposed by CEOS, the Committee on Earth Observation Satellites that I mentioned before, and the Coordination Group on Meteorological Satellites. So CEOS and CGMS came together to produce this roadmap, and the goal really is to coordinate efforts to deliver CO2 and methane products from these space-based measurements in response to stakeholder needs. So the key here is to be able to support international greenhouse gas science, inventory policy, and the regulatory communities. I've spoken primarily about OCO2 and OCO3, but we have a growing wealth of observations from a number of satellites that were in orbit, currently in orbit, and that will be in orbit soon. And this picture here shows some of these assets. We have global mappers, so the yellow colors are global mappers like OCO2 and OCO3, GOSAT that gives us this global picture, but we also have facility scale plume monitors that are designed specifically to measure emissions from oil and gas facilities. We have a mix of public and private missions. GHGSat is a private Canadian company that has launched a constellation of satellites in orbit. Initially, they measured only methane, but now they measure both CO2 and methane. So with this growing wealth of space-based measurements, we now have, with this roadmap, a way of coordinating these products to better address the needs of the stakeholder community and to also drive the science. So I anticipate that as new missions come online, we're going to see much greater advances in our understanding of the global carbon cycle, and hopefully also be able to more effectively contribute to future global stock takes and play a role in driving climate policy. So with that, I'll stop and take any questions. Thank you. No, it's good.
Okay. All right. Thanks. I want to thank Dylan for a fantastic talk. Getting into the heart of what's driving a whole community of scientists, and I think you're getting a flavor for the amount of attention to detail and to the quality of the data and the vast range of data that's there. Putting that all together is an incredible challenge, and I think you really articulated that extremely well. So now some time for some Q&A. We have actually part of the Wilson lectures that I love is that it does give us a nice time for discussion. So I cannot really see you very well, but we've got Crystal out here with that mic, and if anybody cares to ask questions, we'll pass you the mic first here because we have people online as well.
Yes, I think you were going to tell us about the impact of Mount Pinatubo.
Yes, excellent.
CO2.
I wish we had door prize.
Excellent, very good. So that drop in the growth rate in the early 1990s is because of the effects of Mount Pinatubo. So Pinatubo was a tremendously explosive volcanic eruption that put a lot of particulate sulfuric acid particles into the droplets into the stratosphere. And those droplets did two things. They reduced the incoming sunlight, so that led to a cooling of the surface for a couple of years. And the cooling of the surface reduces respiration. So that reduces the rate at which CO2 is released to the atmosphere from respiration in soils. The other thing that it did is in reducing the amount of direct radiation coming in from the sun, it actually enhanced the diffuse radiation. And that is very effective for photosynthesis. So the plants were able to better take advantage of that diffuse radiation to enhance photosynthetic uptake. So you had more photosynthetic uptake, less emission from respiration, which resulted in more of the emissions from fossil fuel combustion being taken up by the biosphere, leading to a smaller growth rate in time. So it was a beautiful experiment in a sense.
We're also trying to keep those online kind of in the loop. So Crystal's getting a workout now.
Is there what's the correlation between levels of carbon dioxide and the average temperature rise, the 1.5 degrees Celsius or whatever?
That's a great question. It's hard to say. There's a correlation. I couldn't quantify it for you, but it's definitely correlated. And we expect that as CO2 increases, the global temperatures have to increase. In fact, I skipped over this animation here, but go to full screen. Sorry, this is not very effective. I don't want to waste your time. But as we go back in time, we can see the changes in CO2 in the atmosphere. Okay? So I'd stop the animation so that you wouldn't see this, but what we're looking at here are changes in CO2 in the ice core, from the ice core record. Right? And this is just tracking the waxing and waning of the ice sheets, the ice ages. Right? So when I said CO2 was at 185 during the last glacial maximum, it was at this point here, when the ice sheets were at its maximum. So on these long time scales, we see a very strong correlation between CO2 and global mean temperatures. And we expect that as CO2 increases, global mean temperatures must increase because it is a greenhouse gas. That's what greenhouse gases do. They increase what we call the opacity of the atmosphere. So it makes it harder for the atmosphere to radiate and cool, to radiate to space and cool, so the temperatures must increase. Now, the amount by which the global mean temperatures will increase for a doubling of CO2, for example, that's a much harder question. And that comes back to something that we call climate sensitivity. And there's some uncertainties there in terms of how much will the global mean temperatures change given a certain change in CO2. There's some uncertainty across the different models for that. So kind of a long answer to your question, but it is correlated, but the degree of that correlation is something that I couldn't quantify for you.
Quick question. In school, I was taught that the drop in the slowing of the CO2 increase in 1991, 1992 was because of a reduction in industrial activity after the fall of the Eastern Bloc. So was that a myth? Because the volcanic explanation does make a lot more sense to me.
So there may have been an impact on CO2 levels from that as well, but you wouldn't expect, if I go back to the growth rate, you can see that this is a fairly short-lived structure feature, just for a couple of years. Right? So you'd expect that if you were indeed seeing an impact due to a dominant impact from changes in the dissolution of the Soviet Union, that would persist for longer. And indeed, when we look at methane, so this is CO2, but if you look at the methane growth rate, there was a significant change in the methane growth rate. And the argument has been proposed that for methane, some of the changes in the growth rate that we saw in the 1990s was because of changes in the Eastern Bloc countries. But there's still some uncertainty there as to whether that was indeed the case. But it's a stronger argument for methane than it is for CO2. The CO2 signals are dominated by other processes.
Thanks. And about the maps you showed of the satellite measurements over the land and over the sea, why do the measurements of CO2 over the sea only exist in the tropics, whereas the land measurements extend into the temperate?
Great question. I wasn't going to go into that just because it's an important detail that is too much of a detail. So I actually had modified my slides yesterday. So the satellites are...
They are in polar orbits, right?
Yes, yeah. So the satellite is looking at reflected sunlight. Right? So you need a fairly bright surface to get reflected sunlight. The oceans are fairly dark. Right? So over the oceans, it's really hard to get a strong signal. And what the satellites do, what we do is instead we rely on glint reflection. So we use what's called the glint mode. So over land, you're just looking at the nadir below and you're making the measurements and you're looking at the reflected sunlight coming back up. Over the ocean, you basically have to look for the bright spot, the glint spot, to get the strongest reflected signal to make that measurement. And that basically places some constraints based on the sun angle in terms of where we can make those measurements over the ocean. And also, the other thing I should mention, sorry, just to be clear, is that, here we've intentionally neglected high latitude measurements because you have issues with retrievals over snow. Because again, you're looking at reflected sunlight. And so you need to be able to characterize fairly well the reflectivity over the snow. And that will vary depending on the age of snow and so forth. So it's a really complicated thing to do. And there are larger uncertainties of the retrievals, these measurements over snow. And so typically we use fewer of those measurements over snow.
Somewhat related to the question about the Eastern Bloc, I guess, but I wondered if during COVID-19, I noticed that it looks as if the graph is a little lower there. Is that, has it been localized for industrialized countries or centers, and is there any actual correlation with a lower activity during COVID-19?
Yeah, so we have seen changes in the greenhouse gas emissions locally and globally as a result of the COVID lockdowns. That shows up in the greenhouse gas record. You see changes in air quality as a result of the reduced transportation during that period. Some really nice work was done here actually at U of T and Professor Kim Strong's group showing the changes in the greenhouse gas signals as a result of the COVID-19 lockdown. So yes, it does show up. We see it strongly in the satellite data.
Thanks. You mentioned a few times you couldn't see through the clouds with the current instruments. Are the future missions compensating for that all? Do we have different measurement technologies, or can ground-based measurement platforms see below the clouds?
Clouds are just a problem. We cannot see through the clouds. So ideally you want to go to much higher spatial resolution to basically capture those gaps between the clouds. It's a problem for the shortwave infrared measurements. For some of the thermal infrared measurements, depending on the opacity of the clouds, you might be able to make some measurements, but clouds are just a problem for remote sensing instruments. And there are a lot of clouds on the planet.
So all of those future missions you were mentioning, those are all shortwave infrared missions as well?
Mostly. So CO2M, for example, those are all looking at the shortwave. So the instruments that are really trying to get at the CO2 signal near the ground measure primarily in the shortwave infrared part of the spectrum. I mentioned that GOSAT uses that strategy, but GOSAT also measures in the thermal infrared part of the spectrum. So we can, and we do have, measurements of methane and CO2 from the thermal infrared part of the spectrum from GOSAT. But if you look at the sensitivity of those measurements, they don't extend to close to the ground. You're picking up primarily variations in CO2 and methane from about 5 to 10 kilometers in the atmosphere. Right. Now, you can, and we have, combined that thermal infrared measurement with the shortwave infrared measurement. Right? And so there's value in doing that because you're getting more vertical information. The challenge here, of course, with this shortwave infrared measurement is that you don't have vertical information, right? You're just getting a vertically integrated estimate. But if you can combine that with the thermal infrared measurement that's sensitive primarily to the mid to upper troposphere, so the 5 to 10 kilometer, you can now get some vertical information. And that's useful in the context of an inversion because if you have fires, for example, you may have emission of the fire, injection of the fire emissions into the 5 to 10 kilometer part of the atmosphere and get transported. And so you can combine that thermal infrared measurement with the shortwave infrared measurement to get more constraints on how the emissions are changing.
Thanks.
I'm going to indulge myself in the last question of the session. And that is to, since you ended on a forward-looking note, which I really appreciated, projecting maybe 30 years from now, 2060, say, something like that, assuming we're all here to witness, and things continue, what would be your vision of, real success in this area of combined satellite, ground-based modeling? What would it look like, and how would it affect society and our understanding of the carbon cycle?
It's a great question. I'll answer that and preface it by saying, I'm an atmospheric modeler, and in particular a data simulation guy. So I work on combining data sets. And so I imagine we'll have a system not that dissimilar from the weather forecasting system that we have right now. So right now, for the national weather services around the world, they are collecting millions of observations every day, integrating them into these data simulation systems. So we're optimally combining models and measurements to give us a better estimate of how the weather system is changing in time. And many of you will complain when the snow forecast is off by 5 centimeters or something like that, but I hope you appreciate just how impressive it is that we're able to make these predictions. And this is being done by collecting millions of observations every day, integrating them into the models so that we can get a much more accurate and precise description of how the system is going to evolve. And I think over time, we will have something like that for the trace gases, in particular for greenhouse gases. And so, the vision is that we'll have a system where we have this suite of instruments in orbit, the information is being ingested into our forecasting systems for carbon. We'll be simulating not just the CO2 concentrations and the greenhouse methane concentrations in the atmosphere, but as well the surface fluxes. So you'll be able to make predictions as to how the fluxes will change in time, and that's something that policymakers can use the way we use weather forecasts right now to guide farming practices, to guide transportation. You can imagine having a predictive system for surface fluxes that you can use as a policymaker to make predictions as to how things might evolve if we make certain assumptions about carbon emissions. So it's really developing this predictive system for both the concentrations and the fluxes in time, given enough observations. And NOAA was working towards something like that, and as part of their carbon tracker system. It remains to be seen whether that will survive the current situation in the U.S.
That torch might get passed overseas or up here, or there might be ways of there, but the knowledge and the ideas are out there. So
I think that is actually, I think, part of the Copernicus vision is to have some kind of a global predictive system like that. And ECMWF, the European Center for Medium Range Weather Forecasting, is working toward that as well. So I should have mentioned that instead of just NOAA. So both the U.S. and the Europeans are working in that direction as well.
Okay, so I think I'd like to bring the session to an end. So let's thank Dylan for a wonderful talk and introduction.